Okay, we continue with battery applications in IPS, which is section 3.4, right? And these times we need to have the battery sizings, right? Why we need to have the battery sizing? Because we know that battery is widely used in the IPS, especially for UPS purpose, UPS purpose, and those UPS will have the so-called the period times, period of times. I mean the operating period of based on the period of time. I mean how long we need to back up our loads when we having the problem of the power outage, or the blackouts, using the UPS. And that's why we need to know about the autonomy times, or we call it as a period of times. Okay, this is the autonomy times. So how much time we need to back up for our load during the outage. And you can look at here, if we don't have the battery sizing properly, then it will lead to some problems. For example, here you have the poor autonomy times. I mean, if we set for 5 hours, so it might only run for about 2 or 3 hours, okay? And it is not according to our autonomy times, because we need these autonomy times to back up our data. For example, sometimes we need 2 or 3 hours to back up our data during the power outage. So if we don't have the proper or sufficient autonomy time, so that means our data might not well back up, might not well backups, and maybe you will facing the permanent damage to the battery cell as well, due to the uh, improper of the battery sizings. So this one is most probably due to the overloads conditions, from the over discharge. And sometimes you will have the low voltage at your load sites, so if you don't have the proper battery sizing. So uh, all in all, you will have a lot of the battery sizings improper. That means the improper size of the battery, then it will give you a lot of the problems, right? So that means we need to have the battery sizing properly, and the method that we use is the based on the IEEE standard 485 for the lead acids, and the standard 1115 for nickel cadmium. So it is based on the ampere hour, or AH. What we understood, the battery, normally if you buy the battery, so the capacity is defined in the mAh, and that one is normally what we can see from our power bank, for example, milliampere hour. But in the IPS, normally we define it as the ampere hour, AH. Okay, so for example, you have the 100 ampere hour or 200 ampere hours. This depends on our size that we need. And there is few steps to be followed if you wanted to consider the battery sizing properly. So of course, the step one will let us to collect data, and I mean the data, I mean including the what kind of loads that we are going to back up using the battery, and what is the power rating, for example, the voltage, and etc. Okay, so we need to have the data collection first. Then after that, step two, we need to construct the load profiling, and the load profiling for our load. And from there we can calculate, we can simply calculate the design loads in VA and the design energy. So energy is always dealing with the hour in this case, dealing with times as compared to the load here. So the load is always defined as the VA or kVA sometimes, but the design energy is VAH or kVAH. And come to the third steps, we need to do the selection for the battery types. So we have basically three types of the battery, as we have seen previously. We have uh, the first one, the most expensive, is nickel cadmium. The second one is the lead acid, and the third one is the maintenance free battery. Okay, but most of the industrial will choose for the lead acids. Okay? The lead acids is due to the is the moderation in terms of the size itself and the lifespan, as well as the cost. And the next step 4 is the select number of the battery cells. Okay? So how many cells we need to consider in series. Okay? So that means how many battery cells we need to connect it in series in order to cope for the for example the voltage. Okay? And of course we can do it in the parallel as well. Okay? So if we seek for the current improvement or the current enhancement. And step 5 is to calculate the required ampere hour, the ampere hour capacity. So this is the capacity of the battery. So these are the 5 steps we need to follow in the battery sizing. It's pretty simple. And we jump over to the step 2. So assume we have the data for the loads in step 1. Then now we jump directly to the step 2. So we need to find what is the design loads. So it is defined as SD. SD. D is the design. Okay, D is for the design. So we need to estimate for the design loads in the S as apparent power, and the energy in E. Okay, and for SD is equal to SP. SP is the peak load, the peak load in apparent power, VA. So plus, of course, we have some factors to be considered. So for example, here we have kg. What is the kg? Kg is the contingency for future load growth factors. So normally we take it as 10%. That means we need to consider extra 10% for this case, just for the future load growth. And another one is the KC. So KC is the design margin, and the design margin. So sometimes when design it, we have a margin due to the temperature, due to the operating conditions of our battery, for example. So that's why we put margins about 10%. So that means we have kg additional 10% and kc also additional 10%. And same to the energy demands. Energy demands, ED is equal to the ET. So ET is the total load energy in VAH. Then we need to consider these two, kg and kc as well. And in the step 3, we need to consider what types of the battery we need to use best to suit our condition of the operation. So first we need to consider the physical characteristics. So how big is the area maybe for placing the battery, for example, right? So the expected life of cells. So how long we need to expect the lifespan of the battery, and frequency and the depth of the discharge. So this is because these two, frequency of the discharge, charging and discharging, and as well as the depth of the discharge will influence or it will give effects to the battery's lifespan. Okay, so that's why we need to consider it properly. So that means in terms of the frequency, that means the higher the frequency, that means if we always charge and discharge our battery frequently, then it will shorten our lifespan. And ambient temperature, so we need to consider, because normally a battery manufacturer is test the battery at the temperature of 25 degrees Celsius. Okay, 25 degrees Celsius, that is the manufacturer's test ambient temperature. If you increase the temperature, of course there is a factor, the temperature factor we need to consider after this. So how much is the duration factor we need to consider if we put it in the higher temperature condition, right? So in general rules, we have to bear in mind, for every 8.3 degrees Celsius increments above the ambient temperature of 25, then the lifespan of the battery will be reduced 50%. okay, because the battery don't like to operate in the hot ambience, and they prefer to have the lower ambient temperature. Especially the ideal one is 25 degrees Celsius, right? So that means if you operate you add another 8.3 means to 25 is 25 plus 8.3, which is 33.3. That means your battery lifespan, you can expect it is reduced about 50%. Okay? And the charging characteristics. So this is interrelated with the third one just now, frequency and the depth of the discharge. Okay, the charging characteristics. So this one is in addition, it also consider the charging circuits that we are using. Okay? And maintenance requirements. So is there any maintenance we required, or if we have not enough maintenance, maybe maintenance staff, I mean we need to seek for the maintenance free battery. So of course it will cost you higher in terms of the cost. And ventilation requirements. So we know that the battery, if the battery is operating 24 hours, so it will lead to the overheat, and of course when you have the a bank, the battery bank, that means a series of the battery, so of course you need ventilations to maintain the temperature, temperature. And another one is the this one is not that applicable in Malaysia. We call it as the seismic factors, and the seismic factor is due to the earthquake due to the vibration and the shock. So that's why in our car normally we have a vibration and shock, and this will give impact, much impacts to our battery's lifespan, as compared to if you don't have the seismic factors like the vibration and the shock all the way its operating conditions. And the most common number of cells that we can have in the market normally is this is the rated voltage. So from 12 volt, 24, 48, 125 and 250 volts, and this is the DC volts, and the DC volts. And if you choose for the lead acids, we can have let's say 12 volt is 6 cells. Okay? So if we wanted to have the higher voltage for example the UPS applications 125 volts, so we can seek for 60 cells, 60 cells of the lead acid. So if we choose for the nickel cadmium types of the battery, then these are the number of cells, the number of cells available in the market based on the rated voltage. And the battery voltage ratings, so this is the typical applications of the battery size based on their rated voltage. For example, 12 volt is normally used for automobile or car. Okay? So 125 volt is for electric substation, and UPS normally for 250 volts. Okay? So we choose 250 volts for UPS. Right, so come to step number 4. Step number 4 is to find out how many cells we need, how many cells we need to connect it in series. So n is the number of cells that we need. So this is the maximum and this is the minimums, and it depends on the voltage, the VDC, nominal battery voltage. Okay? So if UPS is 250 volts, for example, and the VL maximum, so the VL maximum is the maximum load voltage tolerance. Okay? So how much the load voltage tolerance is depends on the let's say the TMB, TMB 415 volt or below. So it allows 10% of the load voltage tolerance. So that means this is 0.1, okay, in that case. And the VC is the cell charging voltage. So how much is the cell charging voltage? Okay? And the same things happen to the minimum side here. the minimum size. So we have the VDC and we have the VL min. At this time we have the VL min. So of course the tolerance is normally plus minus 10%, for example. Okay, so of course this is the 10% as well, but this time is the minus. Okay, this is minus. So if the minimum voltage tolerance is 10%, so plus minus 10%, so don't put minus 10 here. Okay, don't put minus 0.1 because we have defined here minus already. Okay, so just put 0.1, okay, even though it is a minus 10%, so just put 0.1 here. And for the minimum, so we need to know about the end of discharge voltage. So how much is the end of the discharge voltage for our battery? And so we need to consider this end of discharge voltage. So end of discharge voltage is the minimum voltage that the battery need to be charged against, right? And the minimum battery capacity, the battery capacity in ampere hour, so we define it as C min. So this is the minimum battery capacity required, the minimum battery capacity required in ampere hour, and it is depends on the E. So this is the energy, the design energy over autonomy times, and we have several factors to be considered here as well. So Ka is the battery aging factor, the aging factor. So normally we use 25% of the aging factors. And Kc, so Kc is the capacity rating factor. The Kc is the capacity rating factor. So normally we take 10% only, the Kc. And the Kt is the temperature correction factor, as I told you just now. So if we place our battery in the hotter area, let's say 35 degrees Celsius or 40 degrees Celsius, then we have to make sure we to key in the correct temperature correction factor here. Okay, so we have a tables for this, and the VDC is the nominal battery voltage. Okay? So the KDOD, DOD is the depth of discharge, So what is the depth of discharge? So normally we take it up to 80% of the discharge. Okay, so you look at here. So the DOD is the depth of discharge, and SOC is the this is for the charging, the state of charge, the state of charging. So one is for charging, so another one is the discharging. Okay, so it is always opposite. When this one is charged is 100%, so it will the DOD will be 0. Okay, so DOD is a minimum level. For example, here if we say DOD is 80%, means we use up the battery up to, the remaining 20% only, then we have to charge it again. Okay? So that means the allowable discharge levels is 80%. Okay? The discharge level maximum here is 80%. So in this case is 35% only. So that means if our battery level is 65, then it will have the auto charge again here. Okay? Of course, this is not recommended, as well as this one also normally is not recommended, especially for the lead acid. So lead acid normally we take 50% only for the lead acid type of the battery. Okay. So what is recommended normally for the DOD is minimum is 40%, 40%, 40 to 80%. Then we have to discharge again. So that means the DOD is 60 to 80. So this is the cell correction factors. So if we place our battery in different ambient of the temperature, that means we have to look at this table. Okay, so this table is defined in the Fahrenheit, degree Celsius, and this is the correction factors. Okay, so this is the continue. It continue from 25.6 here. So basically it's defined in the Fahrenheit. Every 5 Fahrenheit, then you will have the correction factors. and this is the where the manufacturer tests the battery at 25 degrees Celsius or 77 Fahrenheit degree. So that's why the correction factor is 1 here. So it start from here 1. So that means if you put the battery at the cooler condition, for example 10 degrees Celsius, then you will have additional capacity of the battery. Additional capacity of the battery is it additional 19% of the capacity. Additional 19%. But in Malaysia, normally if we have a hotter ambient temperature, for example, we place our battery at 30 degrees Celsius or even higher, then we'll have the rate factor. So that means we have lost some of the capacity. Even though we buy at 1, but we only can use up in here is 95.6% only. Okay? So if we place at 40 degrees Celsius, so even worse. So we lost about 10% of the capacity. Right, the DC current rating of the battery charger. So this is for the battery charger. Okay, so this is the battery charger A. So how much is the current rating? How much is the battery charger current rating? So it's defined in A here. So it's 1.1 times ampere hour. Ampere hour is the recharge in ampere hour. So how much ampere hour will be recharged at that particular time? And T is the recharge times. Recharge time. So of course, the longer recharge time, the smaller of the ampere here, the smaller current we need for charge the battery, because we take a longer time to charge. Okay? And the L is the DC continuous load currents. It is defined in ampere. So how much is the continuous load currents required by the load? Okay? So we have another two factors to be considered here, C1 and C2. So C1 is the temperature correction from the manufacturer, and C2 is for the altitude, the altitudes where we place our battery. For example, if you place the battery at the Mount Kinabalu, for example, so the altitudes there is about 4095 meter. Then you have the correction factor for that particular altitude. So we look at the example 3.2. So calculates the DC current rating for the battery charger. Okay, so now this is a very simple calculations. So we need to find what is the A just now. Okay, so the recharge times required is 8 hours for this battery. The continuous load current is 5 ampere. The maximum ampere hours of discharge. Okay, so we only need to discharge 150 ampere hour. Okay, 150 ampere hour. And the maximum ambient temperature is 55 degrees Celsius, and that's why it resulting in C1. The C1 is the temperature factor, correction factor, which is 0.8. So you can refer to the table previously. And the altitude is 1,500 meters, is resulting for C2. The C2 is 0.9. So with this data, then we can simply calculate how much is the current for the battery charger. Okay, so it's 1.1 times 150 ampere hour divided by 8 hours plus continuous currents, and the temperature factor and the altitude factor as well. So in this case, we only need 3.56 ampere for the charger current. Right? And we go to the UPS, so because the battery sizing is the next will be the UPS. So battery sizing is one of the one of the hearts that we need to consider for UPS. The UPS is normally, you know, that is a uninterruptible power supply. Even our computer also we have the UPS sometime. And it is normally for backup, for backup or for the power quality improvement, especially the voltage and the voltage quality improvement. So these are two important roles or important function of the UPS in UPS. So one is to have the the backup supply, another one is to correct the voltage quality, in the IPS. So in order to fulfill these requirements, so we need to have the static transfer switch. We need to use the static transfer switch. So this switch is switchable from the our main incoming supply, let's say from the TMB AC, or if our TMB is facing some problem, or the power outage problem, then this transfer switch will automatically switch to the battery, the battery or the inverter here. Okay, so it's like here. So you have the input AC mains, then of course you will have the AVR, the filtrations. This is the transfer switch, and this is the transfer switch. This is going to our loads, and this is the from our UPS. So this is our UPS system. It consists of the rectifier, the battery, and the inverter. So once we have the outage, we have outage from our mains, this switch will automatically switch to the inverter here. Yes? It will switch to the UPS. So basically we have three types of the UPS. One is the online types, another one is the offline, and finally we have the line interactive types. Okay. And online is normally based on the implied by the name online UPS. That means the UPS is always the main power supply. Okay? That means our load is always supplied by the UPS, and in this case the main AC mains, let's say from TMB, is just our backup. Just our backup or power supply number 2. So in case we having some problem in our inverter or the rectifier, then we couldn't perform our UPS, then you only switch to the main AC supply here, from the TMB. Otherwise it is keeps supply from the UPS. So this is the online or double conversion UPS. And the line interactive UPS is it is connected in parallel, both are operating together, right? And in this case the main purpose of this line interactive UPS is to improve the voltage quality, because most of the time in the IPS we facing the voltage quality from our incoming the mains. So that's why no doubt we need to use the UPS to correct some of the voltage quality. It is not that severe. If the severe condition of the voltage quality, we also cannot use the UPS to correct it. Rather we need to use other devices to correct the voltage. For example, we have the AVR, we need to correct the voltage, or we have the reactive power compensator to correct back our severe voltage quality effect. And finally we have the offline or the passive standby UPS. Implied by the name, it is just for standby purpose. Okay. And in this case our load is taking the supply directly from our mains incoming, and the incomings. If our incomings having the problems, for example the blackout and etc., then it only switch to the UPS to operate it. This kind of the configuration normally is designed for low sensitive loads, such as the personal computer and etc. Okay, after we have seen the battery sizing and the size of the battery, and we can apply that in the UPS sizing as well. Apply almost the same thing, but this time we embed the battery sizing into the UPS sizings. That means battery sizing is one of the step in the UPS sizing, but more or less it's about the same as the battery sizing. So we look at that. The step one is to prepare the load list. Okay, we need to have the load list. Okay, which type of the loads and what is the number of the loads that we need to back up by the UPS. It is considered the apparent power. Apparent power at S is equal to the P divided by the power factor times the efficiency here. And we need to know about the autonomy hour for our to back up our load as well. The autonomy hour is very important in this case. So step 2 is to construct the load profiling. So we need to draw the load profiling in this case. So we'll have one example later on to see this one. And step 3 is to calculate the peak design loads. We need to calculate what is the peak design load, in kVA, so that we won't lose the power. We always seek for the peak design load, so that we won't get the any power outage or not enough power later on, and the design energy demand as well, in the kVAh. So it is the same like the battery sizing. So SD is the SP1 plus kg. Another one factor is the KC. We need to consider. I mean, the future load grows 10% and the design margin as well. Because we designed this one for future, it is not for the moment that we need to use it only. It might be for 5 years. That's why we need to consider the load growth, about 10%, and the ED as well. And step 4, that's why I told you that the battery sizing is embedded into the UPS sizing, because step 4 is for battery sizing. That means we need to repeat again for the battery sizing, then we just put inside here. And step 5, of course, we need to know, after we have selected the battery size, then the next step is the rectifier, or the charger size. Okay, so the design DC load currents is defined as ILDC. So this is the DC loads, is equal to the S divided by VDC. So VDC is the nominal battery or the DC link voltage. So S is the UPS ratings, how many kVA. So it's based on the previous. Just now we have the peak design, the peak design power S, and the maximum charging current. The maximum charging current IC is equal to the CKL divided by TC. TC is the minimum battery recharge times. So how much time we need to recharge it again. And C is the selected battery capacity, the C H, as we have identified in step 4 in the battery size. And the KL is the battery recharge efficiency, a loss factor, and normally we consider 10% for this case. So that's why we need to have 1.1 here, 1.1 here. And the total minimum DC rectifier or the charger current is IDC, because our IDC is divided into 2. So one, it will drain to the battery, which is IC. IC is the charging currents. Another one is from the rectifier. Sorry. So that's why we have IDC in the total. So we have the LD. Sorry, this is LDC is drain to the loads. Sorry, so it is from to the loads. This is from the rectifier. So it's divided into 2. So one will drain to the loads, another one will drain to the battery. So that's why we have 2 for the rectifier. This is for the rectifier DC current. And finally, in the step 6, we need to find the inverter or the static switch size. So how much is the inverter size we need? And for 3-phase, of course, we have S is equal S divided by Z3 times the V naught. V naught is our AC supply. V naught is our nominal AC supply voltage. And for the single phase, of course, it is only S divided by V. S divided by V here. Okay, we look at one example, example 3.3. So you have in an inverter based UPS, we have an inverter based UPS installed in the factory to run 10 nodes of 250 VA. 250 VA ESD. ESD is the electrostatics device, electrostatic device cabinet for at least 3 hours. For at least 3 hours during blackout. So that means our autonomy hours is 3 hours. So how many load we have? We have 10 nodes of 250 VA of ESD. And the battery bank output voltage is 120 volts DC. So this is the battery bank voltage 120 VDC, and the future growth and the design margin is considered as 10%, both considered as 10%, which is kg, and another one is what, kg and the kc, I think, right? And the cells charging voltage is 2.25 volts DC per cell. So one cells it will contribute 2.25 volts. And this is the end of discharge, EOD, end of discharge voltage is 1.8. So that means end of discharge, once the cells is dropped to 1.8 volts, then we need to charge it again. We need to charge it again because the charging voltage is 2.25, and this is end of discharge. And the minimum and maximum load voltage tolerance are 10% and 20% respectively. The minimum is 10%, maximum load voltage tolerance is 20%, which is for positive is 20%, and the negative load voltage tolerance is 10%. And we need to decide how much is the number of cells in series. And B is given a DOD. DOD is the depth of discharge is 80%. So battery aging factor 20%, temperature correction factor at 30 degree is 0.956, and the capacity rating factor is 10%. So we need to compute how much is the minimum battery size in ampere hour in this case. So we look at A first. A is very straightforward. So we need to find how much is the maximum cells and the minimum cell in this case. So the maximum cells, so we have VDC is 120 plus 0.2 because the maximum positive or the maximum allowable voltage tolerance is 20%, and the minimum is 10% here. So minimum is 10% here. And the VC is 2.25, and end of discharge voltage is 1.8. So that's why the number of cells maximum is 64, sorry, and the minimum is 60 cells. So normally we will take in between 60 to 64, then we choose 62. So please don't choose for the odd number, so because normally it is in pair, then the best is we choose for even number. In this case 60 to 64, we choose 62 in between. And for B, we need to find what is the energy. So the energy, we have 10 units of the ESD just now, 10 units, so each unit is 250 VA, and multiply with 3 is the autonomy hour. We need to back up it for at least 3 hours, and this is the kg. Kg is the so-called the future growth. The future growth is 10%, and this is the design margin 10% as well. So in this case we have to have the ED is 9075 VAH. So energy is always in the H. We have the time. And the minimum battery size is C min. C means is the ED. So ED is from here. So it's 9075 times 1.2. So 1.2 is the KA, and KC is 1.1, 0.1 here, KC, and Ka is 0.2, and the KT is the temperature factors, correction factors, and VDC is 120, So KDOD is 80%. So from here, we know that the battery size that we need is 119 ampere hour. 119 ampere hour. So of course, if like this one, 119.29, so normally we will round up to the higher one. So let's say 119.29, then we choose 120 or 125. So it depends on your requirement. So of course, when you choose for higher, then the cost also will be higher. So normally we will choose for the closest, one step closest than the final answer here. 119.29, that means we choose 120 ampere hour. And okay, then for example 3.4, okay, so we need to refer to the table E 3.4. that means we have the critical loads and a series of loads, like this one. So we have series of loads. So we have 1, 2, 3, 4, 5 loads to be back up, and each load will have different autonomy times. Okay, for load number 1, distributed control system cabinet, so the autonomy time is only 4 hours. The second is 6 hours, 8 hours, 2 hours, and 4 hours, and etc. Okay, so these are the number of the device that we need to back up. Okay, so 10, 10, 3, 5, 10, and these are the rating in the VA. Okay, we look at back the questions. So the question is we need to construct the load profile, which is the plotting VA versus the period in hour. This is the autonomy hour. Okay, VA versus the autonomy hour for the UPS loading. And this is the task number 1. Task number 2, we need to compute the peak design loads and the design energy demands. If the future growth, contingency, and design margin are both considered as 10%. Okay, then finally we need to design the UPS based on the ratings of the battery bank, okay, and the rectifier system, as well as the static switch and the inverter system. Okay, let's go for this one is the one diagram, the block diagrams, the block diagram of the prescribes the UPS system. Right? So we have the rectifier, so we have inverter, and we have the battery in between. So that's why just now we have the IDC here. IDC is from here, from the rectifier, and then one will drain to the battery, which is the IC, and another one will drain to the inverter, which is the ILDC here. And this is for DC loads. And we have the static switch to switch between the UPS and the AC supply here. And what we require is 415 volts for AC output here. And these are the factors that we need to consider for the battery. Okay. For example, the output voltage is 120 VDC, the DOD is 85% in this case. The battery aging factor is 25, temperature correction is 0.956, capacitor rating factor is 8%, recharge efficiency factor is 1.1, and minimum recharge time is 3 hours. Okay? Minimum recharge time is 3 hours. That means we need to recharge it within 3 hours only. Okay, this is the load profiles, how the load profile is look like. So normally we begin with the lowest one. The lowest one, we begin from the lowest one. We take the longest autonomy hours. The longest autonomy hours, if we look at back the load here, so we have the longest is 8 hours. 8 hours. And how to fit the VA is very simple. So the VA is 180 times 3, which is 540. 540. So that's why in this case this is not according to the scale. It's not according to the scale. So this is just a rough draw only. So this is 540. So up to here is 540, and we have the autonomy hour is 8. And we go for the next is the second highest of the autonomy, which is 6 hours. So 6 hours, so how much is the VA? So it is 400 times 10 units, so that means it is 4,000, 4,000 VA. So that's why from here to here is 4,000 VA. So from here to here is 4,000 VA, and etc. Then you can go back to the load and see each of these loads. Okay, after that, so we need to have the peak design load. So this is what we calculated just now: 540 times 4,000 times 3,005, 1,005, 600. Then the total is 10,000. 10,140 VA. And the total energy demands, that energy you must multiply with the autonomy hours, autonomy times. So in this case, 540 multiplied with 8, and 4,000 multiplied with 6 hours. We need to back up at least for 6 hours for this loads. So that means we need to know what is the total energy demands here. So if you total up, then we have 49,520 VAH. This is the total energy that we need to design. So the design energy demands, so if after we consider the future growth and the design margins 10%, and then at the end what we need is 59,919 VAH, instead of 49,000 here. So we take this figure just now, 59,000, to choose the battery sizing. The C minimum. So what is the minimum size? So of course you can go for highest. You can go for higher rating of the battery size. So this is the minimum. So minimum is the this is the ED, and multiply with 1.25 after we consider the KA. And the KC is 8%, and the KC 8%, and the KT is this one, and VD 120, and KDOD is 0.85. So from here we understood that the battery size, the minimum battery size we need is 758.15 ampere hour. 758.18 ampere hour. So we need to choose the higher one. So of course we can choose 800 to the ease of the calculation. So we choose 800 ampere hour as our battery bank. Now we come to the rectifier size, rectifier sizing. So same thing, we need to know the design loads. The design load we can take from previous one, 10,000. So we consider the load, the factors, the margin, the design margin, and the growth as well. So it comes to 12,000 here. Then of course we choose for the higher. In this case we choose 15,000 VA. Of course you can choose for 13,000 or 14,000 as well. There is no wrong in this case. And the design DC volt, the DC currents, the DC currents. So this is for the load, the design DC load current, and the design DC load current. So it's depend on our loads. Just now is this one, rectifier size. So from the rectifier size, we know that the load is 15,000, and that we choose divide by the DC voltage. DC voltage 120. That means our load needs 125 ampere. Our load is needed 125 ampere. And for the maximum battery charging currents, this is for IC, the IC, the charging current that drain to the battery. So it is 800. Just now we choose the battery size is 800 ampere hour, and multiply with the factors, divide by 3. Divide by 3 is 293.3. So that's why we know that the minimum DC rectifier currents from the DC is the load current plus the charging currents. So 125 plus 293, so it's 418 ampere. So of course we can choose for higher, which is 420 ampere in this case. This is for the rectifier current. And finally, we'll look at the inverter and the static switch size. Okay? So our output, the target output is AC voltage 415 volts. Okay, the three phase. So that's why our design AC load current should be 15,000 VA divided by 3 times our AC voltage 415. We only need 20.87 ampere of the AC load current. So that's why we choose for the higher. Say that we can choose for the inverter of 30 ampere of the rating. Okay? Same to that the static switch, especially the static switch, we need to have the higher rating, because when we switch from let's say the AC mains to the UPS, then it will have the arcing. It will have the arcing. So this is the beauty of the switching and the static switch, because it will have the so-called the arcing voltage eliminations treatment on that. So it is quite expensive for the static switch. So what we need in this case is 30 ampere. Okay. Right, I think that's all for sorry, this is not chapter 1, it is for the chapter 3. Right, so I think I have covered all the chapter 3, right?